So I just wanted to kind of introduce this topic of matroid intersection. So matroids, as we saw, those are very useful if you're trying to do like greedy algorithms. Whenever you have a matroid, yeah, greedy algorithm is going to be the best thing. The the thing is, though, like, okay, matroids are pretty general. There's a lot of different matroids, but there's a lot of things that just aren't matroids that we might want to like solve using where we want to solve problems using methods that are not algorithms. So this is going to connect matroids to some other things. So yeah, so I guess so there are many things, I guess. So there are many problems that are not represented by matroids, so are not on, let's say, on matroids, on a matroid, but can be kind of represented by the intersection of two matroids. Okay, so like instead of trying to find like a maximum weight independent set in a matroid, you might take like for example, find so this is like an example of a problem. Find the largest set y, which is in I1 intersect I2, where let's say x I1 and x I2 are matroids. So it would be useful, therefore, if this like kind of expands the type of problem we're able to study, it'd be useful to have some kind of theorems or some algorithms that can deal with this kind of maximization problem when you're in like the intersection of two different matroids. Okay, and this generally will not work with the greedy algorithm, right? Because we know greedy algorithms, they only work on matroids, at least for all weight functions, they only work on matroids. Yeah, so let's think of it. Let's come up with an example of a problem like this. It's actually like one of our favorite problems from the course, which is matchings in bipartite graphs. Yeah, so if I let so I'll just say the set of matchings in a bipartite graph. First of all, this is not a matroid. So it does not form a matroid. And the way you can see that is like, well, I mean, one reason it probably doesn't form a matroid is we had all of these kind of, not too complicated, but like kind of sophisticated methods for maximizing matchings in bipartite graphs. We had the Hungarian algorithm. And that wasn't just a stupid like greedy algorithm. It wasn't just like, oh, you should just pick the biggest weight edge and then pick the next biggest one. It wasn't just greedy, right? We had to do something else. And like you can just also just give an example. So let's say I take the graph G, which is this bipartite graph. Right, and suppose I take like the pair E of G, comma, I don't know, script M, where M is the set of matchings in G. Then like if I take the set, if I take Y to be the set containing the edge BD, and I let Z be the set containing AD and BC, right? then yeah, this would violate the property of being a matroid. Because if I take this edge in my matching, there doesn't exist any edge in this set that can be added to that to get a bigger matching. Because obviously if I take this edge, it won't be a matching. If I add that edge, it won't be a matching, right? So if you want to get a bigger matching, you can't just take a matching and add something to it. You usually have to do some kind of like augmentation algorithm. So here I could get a bigger matching by kind of alternating these edges. But in a matroid, you need to have. So anyway, so it's not a matroid. But let's see that it can be represented as the intersection of two matroids. Yeah, maybe I'll stay over here. So you guys don't have to look completely backwards.
You're just going to watch through the screen?
Oh, yeah, okay, watch through the screen then. Okay, yeah, fine.
No one's going to be looking.
Yeah, watch me on TV. Yeah, fine. I can watch myself on the screen too. Let's see that it can be represented as an intersection of two matroids. So yeah, let G be a bipartite graph. With bipartition AB. Okay. So what's the rule for a matching? Like it's, any two edges of the matching can only have one endpoint, sorry, they can't have any endpoints in common. So they can't intersect. If you think of a bipartite graph, that means that two edges of the matching, they can't intersect on the left side. They also can't intersect on the right side. So I can kind of represent both of those conditions with kind of a separate matroid. So I'll let I1 be the set of all, let's say Y, which is a subset of E of G, such that each vertex of A is incident to at most one edge in Y. So right. So these are sets of edges that they could intersect a whole bunch over on the right side, but they're not allowed to intersect on the left side. If you think about it, if I take E of G, comma I1, if you think about it, it is a matroid. It's actually something called a partition matroid. But I'm not really saying exactly what that is. But yeah, why is it a matroid? Take two sets Y and Z in I1. So Y will have some edges going to some vertices in A. And let's say Z is bigger than Y. So if Z is bigger than Y, and they're both in I1, there's going to be some vertex in A that's incident to an edge of Z, but not Y. And I take that edge and I add it to Y, and it would still have the property. So it's not hard to see that this is a matroid. Just check the condition. And then similarly, I could let I2 be the same thing. So it's except for B, so sets of edges such that each vertex in B is incident to at most one edge of Y. Okay, and then if I take I1 intersect I2, that's just going to be the set of all matchings in G. Okay. Because yeah, it sets that don't have any common endpoints on the left or on the right, so they don't overall. Yeah, so this is maybe just a bit of motivation. Why do we care about intersections of matroids? It's because, well, if we can learn things about intersections of matroids, well, we could probably prove Koenig's theorem again. Okay. And it also like gives you a more general context. I guess you can solve probably other problems as well. Okay. So yeah, let me give you now state a theorem that we'll prove, I think probably next week. So this is called Edmonds Matroid intersection theorem. So it says so I'm going to take two matroids with the same ground set, so xi1 and xi2 be matroids. So then, okay, so basically my goal is to find like the biggest set that is independent in this matroid and that one simultaneously. So I want to find the biggest thing in the intersection of these collections. So the max of the size of y such that y is in I1 and I2. So for example, the biggest matching in a bipartite graph. So this is going to be another one of these like duality theorems where the max of something is going to be equal to the min of something else, where these things don't necessarily look related. So the max of this is going to be the minimum over all ways of partitioning the ground set. So I'll write this as like A disjoint union B equals X. But by this, what I mean is partitions, all ways of partitioning, you know, X into two sets. I'm realizing now I should give these matroids names. So let's, well, I'll call the first one M1 and the second one M2. We haven't talked about rank very much, so maybe I'll tell you what this. I'll remind you what this was in a second. But this is the rank in M1 of the set A plus the rank in M2 of the set B. Yeah, maybe so a reminder for in any matroid, the rank of a set in a matroid M is the maximum size of an independent set that's like contained in that set. Right. Okay, so this is like, yeah, this is very much like a strong duality type of theorem, right? Okay, it's trying to say, what is the size of the biggest common independent set of two matroids? Well, it's the minimum of the overall partitioning. Like you want to break the ground set into two sets to minimize the M1 rank of the first set and the M2 rank of the second set. And somehow this problem is completely the same as this problem, right? If I compute this minimum, it's the same as that maximum. They're the same problem. Okay. I guess, yeah, if we're thinking about Koenig's theorem, right? If these are like the I1, I2 over there, so this would be the matching. And like somehow that's got to be then the minimum size of a vertex cover. It turns out if you think about those Matroids over there, yeah, that it is going to be a vertex cover. It's going to be the size of the smallest vertex cover. Somehow this is going to, the A and B don't really correspond to those A and B, but anyway, maybe it's an exercise to think about that. It's probably in your assignment, so I shouldn't say anything more. Okay, so maybe I'll just say maybe a few little things. So this is like a strong duality thing. These are exactly equal. Just like with linear programming, the weak duality is much easier to prove. So let's just see why. Why the inequality holds. Why this max is at most that min. Let's see if I remember it. I don't know. I don't think I wrote this down. So I mean, I guess let y be in both of these things, and let AB be a partition of X. So yeah, to show that the max of this is at most the min of that, I just have to show that it's the same thing as showing for every independent set and for every partition, this size of y is less than or equal to that, right? So, because it's the same thing as proving it for the max and the min, because it has to be true for all of them, right? Because if this was violated, this inequality was violated even once, then it wouldn't be true, right? So, so then, okay, this is actually kind of easy. The size of y is the same thing as the size of y intersect A plus the size of y intersect B, because it's a partition. But because this is a matroid, it's downward closed. So since y is in I1, for example, we know that y intersect A must be in I1. And since y is in I2, we know that y intersect B is in I2. But then obviously this is an independent subset of A, an independent subset of B, and the rank is like the biggest one that's in there. So therefore, the size of y is going to be at most the M1 rank of A plus the M2 rank of B. Okay. So the magic thing is that like these just end up being the same thing. Okay. Any questions about that? Yeah, so, I should also add to this. So not only will we prove this theorem, but, so moreover, we will prove that the maximum, common independent set of two matroids, so this quantity here, can be found polynomial time. Okay, so not only will we prove this theorem, but we'll prove that you can actually do this efficiently. Which is like a common theme. When you have a duality theorem, like often it turns out that it also kind of gives you, well, it doesn't give it to you, but it comes with often a polynomial time algorithm. There is one asterisk here, one kind of caveat, which is, okay, it may not actually be a polynomial time algorithm. So it's polynomial time kind of assuming that checking whether a set, let's say Z in X, like a subset Z of X, is in I1 or in I2 can actually be done in polynomial time. So like it's polynomial time kind of, well, like kind of under that assumption. Because like actually, if you have a matroid, it's not actually clear if I can actually check whether a set is in that matroid or not. Because the collection I might have exponentially many elements, so I can't just like look through all of them and say, is Z in there or something. So I mean, like it's, but for something like these matroids over there with the bipartite graph, it's pretty easy, right? You just check, it's a bunch of edges, you just check, do they have a common endpoint on the left or the right or whatever? So that's pretty easy, but generally it's not obvious if you can always detect whether it's in I1 or I2 quickly. But so basically this is going to be a polynomial time algorithm where like it does a polynomial times number of checks whether a set is in